How far is it from infinity back to the nearest normal number? It's like outer space. Starship is leaving one galaxy going to the next one, and there's a big distance there. How far apart are they? Uh, it happens in real space, and it happens in floating point IEEE numbers. They're really odd when you get into the large ones. Okay, so they wanted, I don't know if everyone wanted it, but the local students wanted to go to GDB, which we'll do. Everyone's ready? Okay. I almost got to remind me where the camera is. Okay. Back there. Today is February 24, and we are at 10 o'clock. So begin. The the second, the third letter is easy. Data debugger, not database. So G is GNU. And the GNU organization built this debugger on a budget of zero. They just volunteers helped build it. You want to believe it. Like NASM is right now on a budget of zero. Just volunteers contribute to the NASM assembler. Okay, so I'm going to split it. We're going to do GDB read only before the midterm. Before midterm. And then the second half will come after the midterm. Read write will happen after read write. Okay, you've probably heard that it's it's not a programming language where you write a code and run this whole code. It's an interactive script that you interact with at every step of the way. Uh, interactive program. Okay, we'll leave it at that. Okay, so first of all, to set up for running GDB, we have to modify the bash file. R.sh. In fact, I recommend you leave R.sh alone and create another one, rgsh. So you open the r.sh in an editor, and then you save as rg.sh and make these small changes on the NASM statement. -f, ELF, 64, et cetera, et cetera, et cetera. At the end, or in the middle for that matter, G dwarf. G dwarf is attached, all one word. In the textbook, the author uses G dwarf number 2. But just in case you read this, it doesn't work for us. Not for us. The author uses not NASM, but YASM, Y-A-S-M. And I have a feeling, without even researching it, that G dwarf number 2 is suitable for use with his different assembler. Just stick with G dwarf. Okay, then G++ statements, you attach a hyphen G on the end. G++, this is compile.
Doing the paper.
Yes. And for linking too, dun, 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 dun. If you're linking hyphen G, and one more modification. At the execution point, it is GDB space dot slash my executable. Okay. So 4 places where you make a modification. On the NASM statement, you add this extra parameter. On the compiling statement, you add this as an extra parameter. On the linking statement, you add this as an extra parameter. And on execution, you prefix it with this on the left side. And then you have a new bash file that enables GDB to run your program. You're running it under control of GDB. Okay. So let's go for about a half an hour, and then I have a demonstration of what has just been talked about. What comes next? Okay. So you do the obvious. /rg.sh. And it goes through some hieroglyphics here, and then it comes out and has a waiting time for you to enter breaks or create breaks. Yes. Breaks. Okay, how do you do that? Over to the side here, let's suppose that main calls triangle. And for sake of discussion, it's sitting in the file triangle dot cpp dot cp. Well, I'm really losing it. Triangle dot asm. Okay, to create a break back here, a break is a stopping place where execution just simply pauses and allows you to interact with the computer, interact with the program. Little b, we enter little b, a space, and a line number. That creates a break in main at line 28. Okay? We can create a break where main begins execution. We can create a break where main calls triangle. And we can create a break inside a called file, but it's a longer syntax. Triangle dot ASM colon 37. Okay. So that last one creates a break on line 37 inside the file triangle.asm. If no file is named, it refers to main back here. So this refers to line 28 of main. This refers to the first statement within main. This refers to the call statement to triangle within main. Okay, make breaks. After you've made a few breaks, you want to run the program. So you enter just the letter R. Runs the program. Runs program. under the control of GDB. I don't think I need to add that, but under GDB control. Okay. Okay, so then comes some navigation inputs. Navigation. To, let's see, N. Start with that one. If we press the letter N, that's short for next instruction. It will advance, it will execute one instruction and then pause. Execute one. If you enter NI, it will simply show you what will be the next instruction without executing it. One instruction. Okay. Show next instruction. S, N is for next. S is for step. Execute. Next instruction. And you'll say, why are there S and N? They look the same. Show next instruction. And C for continue means execute continuously to next breakpoint. And then it will stop and wait for your interaction with the system. And Q is quit the program. So, now, there's an S and an N that are very similar, except for one big detail. Okay. Here's main. And here it calls something triangle. When the call statement occurs in main to triangle, N refuses to enter into triangle, but S will. So N does not enter. By that I mean it doesn't debug called functions. Yes. Called functions. But S does enter called functions. Called functions. Okay, so if you're if you're sure there's no bugs in triangle, but you're getting seg faults somewhere else, you probably don't want to debug something that's known to be good. So you would just pass by pressing N. N executes the call function, but it doesn't step you into it so you can walk through it line by line. S does the opposite. S executes line by line here. When it reaches a call to a function, it continues inside that function, executing line at a time. So if your bug is here, if you're pretty sure it's here, you have to use S to get to it. But if it's back here and you're sure this is clean programming down here, then you'd want to use an N. N does execute the called function. It simply doesn't take the user yourself into that called function. It executes the called function, but does not debug the called function. Okay, so what does that have to do with the price of cheese on the moon? Just think of printf. Move RAX 0, move RDI integer form, move RSI R15. We're going to print an integer, call printf. So you're debugging code and you walk through using an N. You press N here, and you press N here, you press N here, and it executes. You press N here, it does what printf says, but it doesn't show you. Printf, the N command does not show you what's happening. Now imagine the reverse of that. You press S. My bed is out of ink. You press an S, and this executes. You press an S, and this executes. You press S, it stops and pauses, and it executes that one. You press S here, it's going to walk inside of the code of printf, which is one of the worst jungles I've ever seen. I've not found a way to get out of it, in fact. So this is a warning. What could happen? Doesn't damage anything, but the only way I could get out of the internals of printf was to quit the program and restart it. Okay, this is a danger point. When you come to somebody else's called function, it's probably recommended, more than probably, it is recommended to use N. You don't want to step through somebody else's code. I could never understand it. I couldn't even get out of it by pressing more S's or more N's. Okay, now you know. Next page. Let's see, and you know, C, letter C is just execute until it means fast execution at CPU speed until you reach a break and then pause and quit. And it does what its name says, it quits everything. Okay. Data typing. You know, we need to know types, and they change on us. D, T, S, A, F, U, and X. Okay, so this is an integer data. This is binary. This is string. I'm not sure what this is used for, but they call it address. This is float. It's float without regard to size. It doesn't specify 64-bit or 32. It's just float. Same thing for this integer back here. That D could be used with 64-bit integers or 32-bit integers. This is unsigned integers. And this is hex. So when we ask to see the data in a certain variable, it's common that you specify how to treat that variable, because GDB sees it as a bunch of bits. Should you treat it as float stuff or unsigned integers or whatever? There's the choices. In regard to data sizes, let's go down here. What we know are quad words, double words, words, and bytes. That's assembly. GDB is known as G, W, H, and B. This is GDB. And you know, this is 64, and this is 32, and this is 16, and this is 8 bits. All right, so it's somewhat confusing at the beginning, but it won't be that bad. These are what we have to use. The problem is here with W and W. It's you just have to remember it. Okay, let's see. Okay, let me go and I'll do a demonstration. Let's look at. Remember, I started out by saying that we'll be read only until the midterm. Okay, so under the camera, how to view data. We'll start with C++. Suppose you have integer k equals 17, and we had float r equals 3.5 and double. St equals 66.9. Okay. GDB works in other languages as well as assembly. So if you're running an assembly program or even assembly that excuse me, you're running C++ that's going to later call assembly, you might want to look at the values in C++, and it would look like this. P is the command to output some value. When it takes parameters, there's a slash and then the kind of parameter it needs. This one simply needs to be told what it is. It's an int. So I'm going to use a D off of that list up previously, a space and a K. Okay. So that's going to output 17. Okay. Now, P with a different parameter, like T, is going to output 100001 for 17. And P slash U K, well, if K were negative, this would have some difference. But K is a positive number. It's simply going to output K is 17. Okay, and P slash X would be 17 in hex, which I think is 1, 1. How about here? Yeah. Just some illustrations of different ways to view 17. Do we have any others that are of interest? I don't know. We could try it. In a few minutes, we'll try it. I don't know what it does. If you say P slash string K, put question mark next to it, and T, S, U, X, and F. This would be really confusing. What if you said, I think that's a float number, show it to me anyway. Okay. Remind me, we'll do actually all these in a moment. What about, so something like R equals 3.5 is intended to be viewed as a float number because internally this is IEEE stuff. So it's probably expecting you to say P/float R, and you'll get 3.5, and P slash, well, I'll try that, P/X of R. That'll be a decimal number, 3.5. That, man, I'm not even sure. But we could try it, outputting it as an integer, P/D R. Because all GDB sees is 64 bits laying there, and it wants to know how the user wants to view those 64 bits. Okay. I think this will make more sense when we actually do it live. The last one was this double P/, the most appropriate would be F. Double is named T. But you'll see it will handle a lot of other weird things. P/binary of T. And that will still produce a string of ones and zeros. We'll see how it works. What else? Okay. There's two commands for viewing. P and X. Okay. P takes one parameter, needs taken from the list back here. One parameter taken from this list. It's the typing or the form that you want to view the 64 bits in. Okay. The second output device is just X, which unfortunately, it sounds like hex format, but it doesn't mean that. It means output something that follows. It needs three parameters. The first one is an integer positive. How many numbers? I'll make it like 3 first. Okay. P has no choice for that. If you use P, you get one number. When you use X, you can ask for 3 in a row. It needs a type in the middle. Let's pick float type. So second parameter. See, the 64 bits sitting in a register or sitting in memory, they're just 64 bits. They don't have a type associated with them until we assign a type. So the second parameter is assigning the type under which you want to view those 64 bits. Third parameter is the size. And that's taken from this list. 64, 32, so 16 and 8. Yeah. And then we can look at, let's do 2 ways. Yes. Think of the top of stack. We can look at P/X. $sign RSP. By the way, registers have to have a $sign preceding them. The machine GDB confuses it and thinks you've declared a variable whose name is RSP, but the $sign says this is register RSP. So this outputs contents of RSP in hex. Okay. But X/1, what should we use? X G $sign RSP. That outputs the contents. I didn't say that right. That outputs the top of stack. This one back here outputs the address of the top of stack. This one dereferences the top of stack and shows you that one number on the top of stack for viewing top of stack in hex, the X in the middle. Okay.
So the PX, the one above it is for an address,
Yes, it will.
but not the
Yes.
content?
Yes, RSP holds an address. This will show you that address of the top of stack.
Okay.
In hex. And of course, do we ever want to see another? X is so familiar. Why not show it as an unsigned integer? So just take those 64 bits and use the algorithm for converting binary to decimal unsigned values and show you that. Now, this is really clever. The one, you don't have to be satisfied with a single number. Why not take the first 5 numbers off the top of the stack? And we'll do that. We'll see that it'll show us the top of the stack, a total of 5 numbers. And very good. Let's see. How about X slash, I want to use RIP. Okay. Let's look at the quad words stored at RIP. That would be 1 XG. Okay. That's supposed to be set together. Yes. Okay. Single space in the middle. 1 RXG. Okay. P slash X RSP. Okay. That's the address. I'm not doing this right. No. Yes. The one below is the address. It's the actual number stored in RSP. Real number. In. Do you mind? Okay, I'll just write it again. Yeah, RSP. Now, PX RIP is a true real number stored in RIP. But RIP, that number will be the address of the instruction that's going to be executed next. But to get to that, we have to use the X command. 1X G $ RIP. This is the instruction itself. At address RIP. Okay, there's a difference. The address is one thing, but what's stored at that address is what this command is showing us. Okay, after a while, so what if you want the starting address plus the next 5 quad words? Sure. Uh, what if I should change the types? Those are also could be considered integers stored there. X/20. Integers are D, G, RIP. And you don't always have to look at them as quad words. X20. D is, that's decimal. Okay. D. What was it? It's called W. Okay. I'll walk through these again so you get familiar with it. Okay. Let's take the last one. We're going to get 20 values, distinct values, separated by white space. 20 distinct values. The first value is stored at the address in RIP. So this is the how many. This is data typing in decimal numbers. Decimal. And the last one is the size of the individual numbers. Now, W is 32 bits. Where do we have that? It's here. The W is the 32 bits. Okay. We're going to do it live. Just give me 1 minute. Well, I think it becomes more human to see it working. This is size. Remember back pointer? RBP. SP. Okay, so he has an ending address, the last 2 digits, 70788088, counting by eights. Visually, we see there are 4 quad words. How do you get if we know RSP and RBP, can we compute this number? So it'd be something like 70, and take the large one minus the small one. 88 minus 70, 8, 1. In hex, that's 16 plus 8 is 24. 24 divided by 8. Those are bytes, by the way. 8 is 3. You follow that? So the distance measured by this is 18 bytes, 18 in hex, which is 24 in decimal. And we do every quad word has 8 bytes. So you divide 8 into 24 and you get 3 and you're off by 1. Turns out you're always off by 1 because when you count things, you count, if you're counting the number of steps you're going to take straight ahead, you don't count 1 as where you're standing. You count 1, the next one after it. So this would be step 1, 2, 3, and he comes up with 3. The Romans used to do this many centuries ago. They never counted. They counted 1 as where you're standing still, and then 2 is your first foot forward, next foot forward. They're always off by 1. Okay. So if RBP was pointing to the quad word in the back, it'd come out correctly. You'd subtract and you'd get it'd be 20 hex. 20 hex is 32. 32 divided by 8 would be 4. Yeah, okay. So we're going to have this issue right now. We use P/D $sign R B P minus R $sign R S P. That tells you that's a divide by 8. That's the formula from back here. If you count, if you do this subtraction, large number, take away the small number, you get the number of bytes. You divide by 8 bytes per quad word, and you get the number of quad words, but you're off by 1, and that's why this is here. We'll try it. For the linker, it is also -G. That's correct. Okay, I need to clear the screen. Okay. So back in the background, let's look at this. Here's the bash line. Focus on -G, hyphen dwarf. Assembly wants dwarf. C++ wants -G. Linker wants -G. And the execution wants GDB. Okay. The simple modification of the original bash file. I'm going to take this down. Okay, so there's a C++ main and an assembly ASM. And just want to verify that it didn't mark out the call statement. Okay, here's the calling statement. If I'm going to go stepping through this, I want to make sure I should use an S at that point. And so that looks okay. And Cosmos is a bunch of junk, but it's a good learning program. So I'll frequently use this guy is a marker. That's a good place to put a break. Is the name of the called function. And we could put breaks on by line number after that. But we'll see how much we can get to in the next few minutes. Let's start a bang terminal. I think we're good here. That has permissions provided by RG. Let's see. Like that larger. There. Okay, the GDB system has started, but the program's not running. It's waiting for breaks. Break at main. And then it responds. Break at Cosmos. And it's, if you want to check what have you done so far, it's IB. And it says we have 2 breaks, and one of them is I don't know what the +4 bytes is, but it doesn't matter. It's inside the Cosmos where Cosmos is beginning. If we wanted to, not last kind is what's the name of that file? It's cosmos.asm. Break COSMOS.ASM colon 25. No, that's not a good sign. That's not a good sign. Well, I must say no. Maybe it's just my dumb mistake. Let's try it again. What if it's no, I can't. No, line 25. Line 12. No. I can't call Cosmos. We'll have to do it next class meeting. No. Let's proceed anyway. I can illustrate 90% of what I've been doing. So I'll fix that for the next time. Let's run the program on. Starting the program. Okay. It says, I've arrived at breakpoint number 1. That's why I paused here. I'm waiting for you to look at it and see that I'm going to execute line 19 next. What do you want to do? So we'll say next. And it did execute line 19 right above the cursor right there. It says I'm going to execute another one. So we'll say S does the same thing. Okay. And it did execute that. I'll put a big sentence here. Okay. And next one more. It's going to declare an array. Arrays are the worst problem I have. Okay, so let's say next. By the way, that array doesn't exist right now. It hasn't been executed. If we try to look at X ampersand, ampersand A. Is it? That's mysterious. Let's investigate. P/N $sign SP. Says the top of the stack is here. Where's the bottom of the stack? It's here. And my A, is that between those? A is E90. E90. I think it is. BP is E60, E70, E80, E90. And then it keeps going, it'd be E90, EA, EB, EC. I can't read it upside down. Anyways, RSP and RBP are two important numbers. I'm trying to subtract mentally the large one minus the small one. The large one ends in E0, and the small one ends in 60. E is 14. Take away 6. That leaves 80. 8 times 16. What is 80? 8 times 16. 16 is 2 to the 4, 2 to the 7, which is 128. That's the difference. Why am I doing this in my head when I have a machine in front of me? Place B, parentheses, dollar sign, large number RBP minus small number RSP, parentheses. 128, that's what I said. Okay. That's the number of bytes in the activation record being used by main. But does that really tell us the number of quad words? I think it's off by 1. Let's find out. P slag back. Okay, the number is 17. 17 quad words computed by that formula. How do we know what if that's right? Well, X slash, I'm going to dump out the entire stack at one time. We're going to put them in quad words, shown in hex, and their type size is G. Okay, so it means go to RSP, dereference the address stored there, which puts you at the top of the stack, and then show in hex quad word size 17 consecutive numbers. Yeah. Stack claims here is 60, but I did top of stack right back here, and it's 60. And bottom of stack, I did that here, and it was E0. There's E0. That's the bottom of stack right there. And if I didn't add the +1, bottom of stack would have been chopped off. Well, plus, I didn't use that. Then it's 16, and then you don't get it all. 16. And we see it, but it's missing its bottom part of the stack because that formula without the +1 is wrong. All right, so what is this? I want to put it back to 17. I really did. I skipped some stuff, but we'll come back to it. The command was size G, but the next size smaller is a 32-bit word. So we can cut all those quad words into double words like such. W. Now remember on the table I gave you, W was second largest below G. You can't see it, but I'll show it to you later. the sizes were G, W, H, and B. So if I change it to size W, let's see, we need more space. 34. Okay. Now, that's the stack from top to bottom shown in double words, which are 32 bits. Now, is that really the top of the stack? Two double words should make a quad word. And you compare against here. And what does it show us? It says, yeah, guys and girls, I am a little Indian computer, because what you thought was first is not first. It's actually here. And the trailing part is first in that order. The next quad word down, here's the beginning part of it, and here's the trailing, the second half of that word. Okay. The whole stack is separated into double words. What's the next one below that? It's H. Take the W out. These are now words. Two words. And we're going to need a lot more space, about 68 of them. Is the top of stack here. It require 4 of them. But of course, to us, it looks backwards, because these are the first 4 digits of the top of the stack. There they are. Here's the next 4 digits, 7FF, and there they are. And the next 4 digits is FFF, W there somewhere. And the last 4 are DFF8. DFF8. Okay. Well, this is getting absurd. What if you want to study your data byte by byte? 68. What do we need? About 140 of these. 140. And size would not be H anymore. The size is B. Okay, well, we won't take the time, but it'll take 8 of these to show one quad word on top of the stack. And if you read it from right to left, it will show up in the proper order across the screen that way. There's something else important to do. There's C++. Okay, C++ was supposed to create for us a value M equal to 5. Let's see where it is. Let's do P/decimal M. Okay, doesn't look right, but M at the time I asked for that the decimal value of M had not yet been created. It's going to be created in the next instruction. So I press M. M has been created. And I'll go back and look at the value of M. And it's 5. That's pretty nice. There's a double. It hasn't been created yet. If you try to look at what's inside of it, it's called X. You got that electronic garbage. This next instruction is created the the X, I meant to say. The X is now available to us. Whoa, I didn't do something right. Decent. Well, maybe that is right. Isn't that an IEEE number? Starts with 400. That's close to 1.0. So maybe I need to change the format of output from X to ordinary float. What's it? 745 is not a binary number. It can't represent that exactly. So it gives you the closest approximation that it's going to use to that. And it came out pretty good. Using bits only, showing you how close I can get, but I can't get it perfectly. Okay, so, oh, what was coming next is, I'll just let's see what happens. Double its outcome. This never had a value assigned to it. Greeting is good morning. Now, I have found strings to be the most mind-boggling of all, and arrays in general, but let's give it a try. That's called the greeting. Next, oh, and it has executed the greeting. Right back here somewhere. What do we know? Well, we could find out, where are you? This greeting. Okay, is it this address? You know, I'd like to, I probably don't have time. If I went to that address, we would find the ASCII values of good morning. Well, let's try P/S address of Google. No, it's not quite it. Nothing like that. But there it is. I should have known that from the beginning. Put down in your compendium that you're building, the command for viewing a string is P/S. The command for viewing the starting address of the string is back here. P/X ampersand greeting. And what are the other choices? This is terrible. How many bits in an ASCII number? I think it's 8. Okay. So a feature or disabling feature of GDB is it drops leading zeros. Those are no doubt the ASCII values of the letters of good morning. How could we see the second one and the third one are identical? Those are the 2 O's of morning. And I forgot what, can't figure them out. So we should be able to do better than T. What could it be? That's probably pretty close. uppercase letters precede lowercase letters in the ASCII scheme. That's uppercase A, and then here is O and R, MNOPQR. What the good? I'm saying that backwards. That's D. Okay. There's ASCII D and then ASCII O. You can follow, and 32 is famous for its blank space. And guess what's at the end of all strings? Isn't that smart? He knows to put a 0 there for us. I think I have to stop. There's one more look at that program and see if there's anything of interest back here. Here's going to go through a loop of stuff. Not got much in it. Okay. I'll have next time I have a better program with lots of garbage declared, lots of floats and then integers and longs and shorts and then arrays of junk. And we have to trace them through and find the corresponding GDB command that will unveil it to us. We want to look at its detail. I'm going to stop, everyone. We are at 11:08, and there's an introduction to what GDB can do for you. Oh, we'll do it after the midterm. If you don't like your runtime values, you can just change them right there in the instant and keep on executing. But that comes, we'll do that later on. I'm pausing. That's an intro to what's coming. Any questions for me? I talk too much. I never pause to so that you ask them. Don't forget the formula.
So for G, you're looking at RSP window, yes. You said it prints the address, right? Not the content of RSP.
No, no. That's the contents of the register, that's all. But the contents is an address. That's not the stack.
Okay.
That's all that we- Then you have to use X/ like that, yes. X/one for one number, X you want it in X, and G is you want to count what of that.
So since RSP is tier to the stack, RSP, but RSP is the actual instruction. It's just the address of it.
Yes, that's your way.
It's like our results are getting, you give me like X and stuff, and I'm still learning. So I don't really understand the results. So. Honestly, it just depends on what field you're thinking about. But I think a lot of this, like, if you do have to do it for work, you would be learning on the job. You'd be annoying your senior for a little bit.